The birth of everything. The Big Bang. Prelude to the beginning. Before the Big Bang, there was no space, no time, and no matter, at least not in the way we understand them. The concept of before is inherently difficult to grasp because time itself did not yet exist. It is a paradox that baffles even the brightest minds, as our entire understanding of events is rooted in the existence of time. What existed in this timeless void? The truth is, we may never know. Our knowledge begins not with a gradual unfolding, but with a singular event, the Big Bang. At the beginning, the universe was compressed into an infinitely small, infinitely dense point, a state that physicists refer to as a singularity. This tiny entity contained all the energy that would one day become galaxies, stars, planets, and life. Yet, at this point, the laws of physics as we know them broke down. How or why this singularity came into existence remains a mystery. Some theories suggest that quantum fluctuations in a larger multiverse may have caused our universe to emerge, but such ideas remain speculative. The Planck epoch, the first instant. The story of our universe begins with the Planck epoch, the first 10 to the power of negative 43 seconds after the Big Bang. At this moment, temperatures surpassed 10 to the power of 32 Kelvin, conditions so extreme that none of the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were separate. Instead, they existed as a single, unified force. This unification of forces created a state beyond our comprehension, governed by quantum gravity, a field of physics that we have yet to fully understand. Scientists theorize that during the Planck epoch, tiny ripples in spacetime, caused by quantum fluctuations, began to form. These ripples would later become the seeds of everything to come, the galaxies, stars, and planets that now fill the vastness of the cosmos. Cosmic inflation. The universe expands faster than light. After the Planck epoch, around 10 to the power of negative 36 seconds after the Big Bang, something extraordinary took place. Cosmic inflation. The universe expanded exponentially, doubling in size at least 90 times in a fraction of a second. Imagine a region smaller than a proton growing to the size of a galaxy cluster in less than a trillionth of a second. This rapid expansion smoothed out any irregularities, which explains why the universe today appears uniform in all directions. However, during inflation, tiny quantum fluctuations were stretched to vast scales, becoming the seeds of the large-scale structure of the universe. These fluctuations would eventually grow into galaxies, stars, and clusters under the influence of gravity. Inflation ended around 10 to the power of negative 32 seconds after the Big Bang, releasing an immense amount of energy. This energy reheated the universe and marked the onset of the quark-gluon plasma phase, a turbulent, hot soup of fundamental particles. The quark era. The building blocks emerge. Between 10 to the power of negative 12 and 10 to the power of negative 6 seconds after the Big Bang, the universe cooled to approximately 10 to the power of 15 Kelvin. At these extreme temperatures, the four fundamental forces began to differentiate. Gravity had already separated during the Planck epoch, but now the strong nuclear force split off, followed by the weak nuclear force and electromagnetism. Quarks, the fundamental building blocks of matter, emerged during this era. These quarks combined to form protons and neutrons, the essential components of atomic nuclei. However, not all quarks found partners. Many annihilated with antiquarks, releasing energy in the process. This slight imbalance between matter and antimatter, with roughly one extra particle of matter for every billion particles of antimatter, ensured the survival of matter, laying the foundation for everything in the universe today. Hadron and lepton eras, matter takes shape. By 1 second after the Big Bang, the universe had cooled enough for quarks to combine into hadrons, such as protons and neutrons. This marked the transition from a quark-gluon plasma to a universe dominated by baryonic matter. Leptons, such as electrons, also became prominent during this time, interacting with photons and hadrons. As the universe expanded, particle collisions became less frequent, leading to the gradual dominance of matter over radiation. This era saw the formation of the first atomic nuclei, setting the stage for the complex chemistry that would unfold billions of years later. Big Bang nucleosynthesis, the first elements. Between 3 and 20 minutes after the Big Bang, the universe cooled further, reaching temperatures of approximately 1 billion Kelvin. At this point, conditions were right for nuclear fusion to occur. This period is known as Big Bang nucleosynthesis. Protons and neutrons fuse to form the lightest elements, primarily hydrogen and helium, with trace amounts of lithium and beryllium. About 75% of the universe's mass became hydrogen, while helium made up most of the rest. Heavier elements, such as carbon and oxygen, did not form during this time because the universe's density and temperature dropped too quickly for further fusion. These heavier elements would later be forged in the hearts of stars billions of years after the Big Bang. Recombination and the birth of light. For the next 380,000 years, the universe remained a hot, dense plasma of ions and electrons. Photons, or particles of light, were trapped in this opaque soup, unable to travel freely. This state changed dramatically during the era of recombination, when the universe cooled to about 3,000 Kelvin. During recombination, electrons combined with protons and nuclei to form neutral atoms, primarily hydrogen and helium. This process allowed photons to travel unimpeded for the first time, effectively rendering the universe transparent. These photons now form the cosmic microwave background radiation, a faint glow that permeates the universe and provides a snapshot of its state at 380,000 years old. Discovered in 1964 by Arno Penzias and Robert Wilson, the cosmic microwave background is one of the most significant pieces of evidence supporting the Big Bang theory. It reveals slight temperature fluctuations that correspond to the density variations that would later grow into galaxies and clusters. The Cosmic Dark Ages. Following recombination, the universe entered a period known as the Cosmic Dark Ages. With no stars or galaxies yet formed, the universe was a vast expanse of neutral hydrogen and helium. Although the cosmic microwave background illuminated the cosmos, this light was too faint to provide visible illumination. During this era, gravity worked to amplify density fluctuations in the primordial gas, slowly forming the first large-scale structures. These regions of higher density attracted more matter, laying the groundwork for the formation of the first stars and galaxies. Evidence for the Big Bang. Our understanding of the Big Bang is supported by a wealth of observational evidence. In addition to the cosmic microwave background, the expansion of the universe, first discovered by Edwin Hubble in 1929, provides strong backing. Hubble observed that galaxies are moving away from us, with more distant galaxies receding faster, a phenomenon known as Hubble's law. This expansion implies that the universe was once much smaller and denser. The relative abundances of light elements predicted by Big Bang nucleosynthesis also match observations. Hydrogen, helium, and trace amounts of lithium found in the universe today align with the proportions expected from this early fusion process. Finally, the large-scale structure of the universe, its web of galaxies and voids, traces its origins to the quantum fluctuations amplified during inflation. Modern telescopes, such as the Planck satellite, have mapped these structures with extraordinary precision, further validating the Big Bang model. The ongoing quest for knowledge. Despite the remarkable success of the Big Bang theory, many questions remain. What caused inflation? What is the nature of dark matter and dark energy, which together account for 95% of the universe's mass energy? What existed before the Big Bang, if such a question is even meaningful? To answer these questions, scientists continue to develop new theories and technologies. The next generation of telescopes, particle accelerators, and gravitational wave detectors promises to deepen our understanding of the universe's origins. A beginning without an end. The Big Bang marks the beginning of time as we know it, yet it is not the entire story. It set into motion a chain of events that led to the formation of stars, galaxies, planets, and life itself. While we may never fully understand the universe's origin, the journey of discovery is a testament to human curiosity and the enduring power of science.